Okay. So again, this is section 8.1, Green's theorem. So I'm going to just first remind you the theorem. So the theorem says the following. Green's theorem. So first we start with some region in the plane. So we have, let's say D, be a closed, bounded region in the plane. And in the plane. So when I say in the plane, of course, that's R2. And with boundary, so this boundary, so the boundary of this region D. So you can imagine you have, so this is your region D, okay, and the boundary of D. So whose boundary? Let's call the boundary of D capital C. So this is the boundary of D. Again, this is the symbol for boundary. So this capital C, which is the boundary of D. So here's the boundary of D. Okay, so this is my C. So C is actually is supposed to be simple closed curve. So so the boundary C consists of finitely many simple closed curves. Okay, so like in this example, your C would be a simple closed curve, right? This one here, this is closed and simple. And as Zivolot said, I mean, if you have a curve which intersects itself more than one time, so for example, closed curve, which is so if, for example, if you have something like this, so this is actually not, this is closed, of course, but it's not simple. Okay, this is not simple. Okay. So simple curve is closed simple curve. It's just you know, there will be no self-intersection except, of course, the terminal and the initial point. Okay, so for here, this point here, this would be like the initial and the terminal point of the curve. Okay, so this one here is simple. Both are closed, right? But the first one is not simple. The second one is simple. Anyway, so that's the boundary of your region D. Now we need orientation, so we need to orient the curve. So you have to orient the curves, the boundary, so the curve C, so that the you know, the region D is on the left. As one traverses C, right? So like here, the orientation would be this one here, okay? Because D would be on the left of your orientation, right? So D is on the left. You can see here, D is on the left. So is on the left as one traverses C, right? So as one traverses C. Now, now you suppose you have a vector field, capital F. So let's say you have some vector field, capital F. So F of xy is equal to, so it's a vector field, but it's in the plane. So it has two components. The first component is some function m, and the second component is some function n. functions of x and y, of course. Okay, so this is a vector field. Throughout D, of course, the region D. Okay, so then what's the Green's theorem? So again, the idea behind Green's theorem give us like a relation between the vector line integral of this vector field along the boundary. Okay, so it's related to the double integral over the region D. So then the vector line integral. So of the vector field F along the curve C, that's the boundary of D. So this is equal. So this left side, this is a vector line integral, right? So this is a one-dimensional. This is one-dimensional notion because we integrate along a curve, which is one-dimensional space, right? And on the right side, so this is actually equal to the double integral over D, okay, of derivative of n with respect to x minus derivative of m with respect to y, dx dy. Okay, so on the right side we have this double integral. Yeah, and this is this symbol here, guys, this circle here, this means that we are integrating along a closed curve, right? So this is because this integral along a closed curve. Okay. Anyway, I think we had probably just one example. So let's do. So the last lecture, I think I gave like 3 exercises. So what we can do is probably we can solve 1 or 2 of them. So let's see. So exercise. So we have the following exercise. So I think the first exercise was the following. So we had to verify Green's theorem where the vector field F would be equal to minus x squared y, xy squared. So that's my vector field. So here, guys, this is, so the first component, this would be your the function capital M, right? And this would be the second function. This would be the capital N, right? So that's my vector field. Right now, what's the region D? D is, I think D was the disk, which is the interior of the circle x squared plus y squared equals to 4, I think. Right. So we have to verify Green's theorem. So what does it mean? So what do we have to do here to verify Green's theorem? Well, we have to compare both sides of Green's theorem, right? So we have the left side here, which is a vector line integral, and the right side, it's a double integral over this region D. And to verify Green's theorem, we're gonna compare, left side to the right side. So they are supposed to be equal, right? I think in the homework, I don't know if you guys took a look to the homework, but I think there are a couple of problems. Let me see. I think it's problems. Let me find the homework. I need to find the homework so I can tell you exactly which problems. Right, let me find the homework.
6, 7, and 8.
Okay, I'm opening the file now. Yes, so as Visivolot said, that will be, yeah, 6. That's you have to verify Green's theorem.
Oh,
Blah blah
and
blah.
7 and
7,
8.
7, 2. Yeah, yeah, 7 and 6. Yeah, I mean, like 8, you can also apply Green's theorem if you want, or you can just it's it's a vector line integral. So either you can apply Green's theorem if you want, or you can just evaluate directly the vector line integral. Yeah, well, at least in the problem 6 and 7, you would have to verify Green's theorem. So this is so this is similar to the problems 6 and 7 in the homework 4. Anyway, so to verify Green's theorem, so first we're going to start with the left side of the theorem. That's the vector line integral. So so step 1. Oops. So step 1. So we need to evaluate this vector line integral over the boundary of the region D. Okay, so I would say the thing here. So what's really important here is to parameterize this boundary. So because like in this integral, I mean, we know capital F, the vector field, right? It's given by the problem here, right? We know it's minus x squared y, etc., right? So that's the missing thing here is really a parameterization of this boundary. So we need to parameterize so this is kind of missing. So we need to parameterize the boundary, the curve C, which is the boundary of D. So now what's this boundary? Well, D is so let's just sketch first D and the boundary of D. So D is just the disk, which is the interior of the circle x squared plus y squared equals to 4, right? So we have this, this is 2 here, this is 2, this is of course x, this is y. So we have, this is our disk, D. So D would be the interior of this circle. So this is my D, right? This is D. Okay. This is my region D. And so the boundary of D would be just the circle, right? So this, so this is just the boundary of D. Okay. It's of course it's a simple closed curve, so we can apply Green's theorem, right? Now we need there's something important here is the orientation, right? So we have to orient the curve so that the D would be on the left of the orientation, right? So you want a D to be on the left, so you have to orient this circle counterclockwise, right? So if you have a counterclockwise rotation here, then D, D would be on the left, right? So like you are on this, imagine you have this arrow here, so then D is on your left, right? D is on your left. Okay, so now, so that's our orientation, right? Now we have to parameterize C. So what's C? C is just the circle. So C is just the x squared plus y squared equals to 4. Okay. Now, how do we parameterize circles? Well, we're going to use, of course, cosine and sine. So if you say, for example, x is 2 cosine of t and y is 2 sine of t. Okay. So then, of course, then x squared plus y squared would be equal to 4. Okay, so this is a parameterization of the circle. Why it's a parameterization? Because we introduced this parameter t. Okay, so that's why it's called parameterization, because we have a parameter, which is t, right? So we are parameterizing our curve with the parameter t. And t is in the interval. Of course, this is a circle, the whole circle. So t is with t is in the interval 0 to pi. Okay, because we have the whole circle. Okay, so that's why it's called parameterization, because we have this parameter t, and then okay. Now you have to be careful. Once you have a parameterization, you have to make sure that the parameterization actually coincide with your orientation, right? So this is an important, and you have to be careful of this. So you have to make sure that that the parameterization coincide with the given orientation. Okay. So, so how to make sure that this parameterization will coincide with this specific orientation, right? We have this counterclockwise orientation, right? So all you have to do, guys, is to see how the points are moving. Okay, so for example, so we have the parameterization here is, so you have this gamma of t, which is 2 cosine of t, 2 sine of t, and we are saying t in the interval 0 to pi, right? Now, for example, if you pick just 2 points, 2 different points. So for example, let's say t is 0, then gamma of 0 is it's actually equal to 2 and 0, right? Cosine of 0 is 1, sine of 0 is 0. Now, so this is my first point, and I'm gonna pick another point. So let's say t is pi over 2. Okay, so then gamma of pi over 2 is, well, cosine of pi over 2 is 0, sine of pi over 2 is 1. So that'll be, sorry, that'll be 0, 2. So what I'm saying here, guys, is that like at time t equals to 0, I am at this point, and I am at time t. Again, think of this parameter t as a time, right? And at time t equal to pi over 2, I am at the point 0, 2. So in some sense, my particle is moving from 2, 0 to 0, 2. So I'm moving from, so this is 2, 0, right? This is 2, 0, and here is 0, 2. So I'm moving, my particle is moving from 2, 0 to 0, 2, right? And that will coincide with the given orientation, right? That's the counterclockwise orientation, right? Because I'm moving from 2, 0 to 0, 2. Okay, so so then this parameterization would coincide with this with the given orientation. Okay, so this is why. So we are moving from 2, 0 to 0, 2, and so so it coincides with the given orientation. Okay. I hope it makes sense to you guys. I mean, please don't feel shy to ask questions, okay? All right, so I got the parameterization, and it's actually the right parameterization because it coincides with the given orientation, right, of the curve of the boundary. Now I can of course I can compute my my vector line integral. Okay, so now we are ready. Once we have the parameterization, then we can evaluate now we can evaluate my vector line integral. Okay. So this would be equal to, so just to remind you the formula, so this is f, the vector field f evaluated on this curve, on this boundary, gamma of t. This is a parameterization of my curve. This is my curve C here, right? Scalar product with gamma prime of t, right? dt. And so t is from in the interval 0 to pi. So this is 0 to pi. Okay. So what's f of gamma of t? Well, so remark here. So f of, I mean, the vector field f is, it's minus x squared y x y squared, right? And gamma of t is, 2 cosine of t, 2 sine of t. Okay. So what we are saying, guys, is that my x now along gamma, my x would be equal to cosine of t, and my y would be equal to sine of t. So f of gamma of t, this is just f x along t, along the curve gamma, along the curve c, and y along the curve c. Okay, so which means that my x now is equal to this 2 cosine of t, and my y is equal to this 2 sine of t, right? So that will be equal to, so x, so this is minus x squared times y, so it's minus, my x is 2 cosine and my y is 2 sine. Okay, so that will be equal to minus, so x squared, that's 4, minus 4 times 2, that's minus 8, so that's minus 8 cosine squared of t times sine of t. Okay, and then xy squared, that will be x is 2 cosine and y is 2 sine, so then xy squared, that will be 8 cosine of t sine square of t. Okay. Is there any question, guys? How I got this f evaluated along the curve C, or along this parameterization gamma? Okay, so once you got f, now I can come back to my integral. So this is, again, this is a closed curve here. So f gamma of t, scalar product. So this dot here means this is a scalar product, because f of gamma of t is a vector, and gamma prime of t is also a vector. Gamma prime of t is supposed to be the tangent vector to the curve gamma of t. So dt, so that would be equal to, probably I need to go to the next line. So that will be equal to integral from 0 to pi. So the vector field f, so that's, we said it's negative 8 cosine square of t sine of t, 8 cosine of t sine square of t. Now, what will be gamma prime of t? Gamma prime of t is just derivative of gamma of t, right? So derivative of 2 cosine would be minus 2 sine, and derivative of 2 sine, that would be 2 cosine dt. Okay, and then you have the scalar product, right? This is, again, this is a scalar product, so we have to multiply the first component, the corresponding components, like the first component here times the first component in the second vector, plus the second component and the first vector times the second component in the second vector, right? So that will be equal to integral from 0 to pi. And so that will be actually equal to 16 cosine square sine square of t plus another 16 cosine square sine square of t dt, right? And then, well, so we have to integrate this. This is just integral from 0 to pi, 16 plus 16 cosine square sine square, that will be 32 cosine square sine square t dt, right? So we have to integrate this cosine square times sine square. Well, you can imagine here you have to use some trig identities, right? Probably, you know, I think the cosine square would be equal to like half of 1 plus cosine of 2 t, and sine square would be equal to half of 1 minus cosine of 2t. So here we're going to use some trig. You know, we can just use some trig identities. Okay. For example, so we are saying like cosine square of t, that will be half of 1 plus cosine of 2t over 2, and sine square, that will be 1 minus cosine of 2t over 2. Okay, so then this is just, so we have this 32. I'm gonna just put out this 32 outside. So this is like 32, 0 to pi, and we're gonna have like half of 1 plus cosine of 2t times another half times 1 minus cosine of 2t. Okay, dt. So this would be equal to half times half, that will be 1/4, times 32, that will be 8 outside. So it's 8 now, 0 to pi. This is a plus b times a minus b, right? This is a plus b here times a minus b. So that'll be a square minus b square, a square minus b square. So that's actually 1 minus cosine square of 2t dt. And then, well, of course, 1 minus cosine square, you know, sine squared plus cosine squared is 1. So 1 minus cosine squared, that will be sine squared, right? So this is 8 times sine squared of 2t. Okay, dt. And you can use again trig identities. Sine square of 2t, that will be half. So it's 8, 0 to pi. So it'll be half of 1 minus cosine, the double of the angle. So if you have 2t, then here we're going to have 4t. Okay, it's twice the angle you have here, right? So dt, and that's actually not that's easy now to integrate, right? So this is just, well, 8 times half, that would be 4, and then integral of 1, that will be just t, and integral of cosine 4t, well, that will be sine of 4t over 4. Okay, so this is evaluated, of course, between 0 and 2 pi, and so the answer would be equal to, of course, sine of 4t. I mean, if t is 2 pi, that would be 8 pi. Sine of 8 pi is just like a sine of 2 pi. It's like a sine of 0, so it's just 0. And sine of 0, of course, is 0. So, so the answer would be just 4 times t evaluated between 2 pi and 0. So that's the answer would be 8 pi. Right? When t is 2 pi times 4, that would be 8 pi. So this is the answer for, I mean, this is the left side of the Green's theorem. Okay. Now we have to compare this left side to the, you know, to the right side. So the right side is given by a double integral. So that this is, it's the double integral over our region D. Okay, so our region D is just the disk, you know, This is the inside interior of the circle of radius 2. So the step 2, so here's step 2. So in this step 2, we have to evaluate the double integral over d of derivative of n with respect to x minus derivative of m with respect to y dx dy. Now, what's m and n? It's just the components of your vector field, right? So your vector field, we said, is I think it's equal to, yes, so minus x squared y and then xy squared. That's my vector field f. So the first component, that's m. That's the function m. So this is m here, and this is n. Okay. So we know how to compute the partial derivatives. That's not a problem. Well, here we have to, find the bounds for d, right? The d is, so I would say the main thing here is to find the bounds for d, okay, which is the interior of the circle of radius 2. Okay. Well, if it's a circle, if it's the interior of a circle, I think the best way to parameterize or find the bounds for d is to use the polar coordinates, right? Your region d is, this is your d. So here's my d. Okay, so if we use polar coordinates, okay, then d is just it's the interior of the circle of radius 2. That means that d is just can be parameterized with the radius by saying if the radius r between 0 and 2, and the angle theta between, of course, it's the whole circle, so angle theta is just between 0 and 2 pi. Okay. So if you use a polar coordinate, of course you can use x and y, but then if you use x and y to to find the bounds for d, then you would have like square root of 4 minus x squared or wherever, but if you just use polar coordinates, you can just say d is can be described with like by saying that the radius is between 0 and 2, and theta, the angle theta, is going to be between 0 and 2 pi, because it's the whole circle, right? So in other words, so what I'm saying, guys, here is that, so this double integral over d of partial n with respect to x minus partial m with respect to y dx dy. So this is over d. Partial n with respect to derivative of n with respect to x. So here's my n with respect to x. So y is constant. So that will be just y squared. And here, be careful, this is minus sign. Okay, so this is supposed to be minus. So here's minus. And now partial m, partial y, derivative of m with respect to y, that will be minus x squared. So minus x squared here, dx dy. Okay, so in other words, this is just the double integral over d of y squared plus x squared dx dy. Okay, now I'm going to use the polar coordinates, as I said, because that's the best way to describe d, because d is the interior of a circle. Whenever you have a circle, you can use polar coordinates. So here I'm going to use polar coordinates. So then if you use polar coordinates, of course, let me just remind you, x would be r cosine of theta and y is r sine of theta, right? That's my polar coordinates. So if you do y squared plus x squared, that's actually equal to r squared. So we have this double integral r squared. Now dx dy, don't forget the Jacobian. So it's going to be now, so dx dy becomes r dr d theta, right? Don't forget your Jacobian. Okay. Now the bounds, well, the radius r, of course, is between 0 and 2, and the angle theta is between 0 and 2 pi. Okay. So this integral is very simple. It's just the double integral of r cubed dr d theta, r between 0 and 2, and theta between 0 and 2 pi. So then integral of r cubed, that would be r4 over 4 between 0 and 2 d theta, right? So when r is 2, so 2 to the power 4, that would be 8 over, 2 to the power 4 is 16, 16 over 4 is 4, right? So that'll be equal to just 0 to pi. This will be just 4 d theta. Well, 4 is just constant, so that will be 4 theta between 0 and 2 pi. So when theta is 2 pi, that will be 4 times 2, that's 8 pi. Okay. So you see, guys, if you compare this answer to the answer in the first step where we evaluated the vector line integral, so they coincide, they are equal, right? So the Green's theorem is verified. Okay, so in the first step when we evaluate the vector line integral, we got 8 pi, and here is double integral, we got 8 pi as well, right? So they are equal. I mean, you can also compare. I mean, the two two integrals. I would say, like in this case, you know, the double integral over d is. I would say it's much more simple because we use the polar coordinates, so it's kind of not really hard to compute. On the other hand, for the vector line integral, it's not that hard, but still, you know, there's a lot of trig identities here you have to use, etc., etc. So, you know, it depends on the problems, but sometimes, you know, the right side of the Green's integral would be kind of easier to compute. Of course, in some other problems, the vector line integral, the left side would be easier to evaluate, right? So it depends on the problem. Like I would say, like in this problem, the right side is much more easier. Of course, you have to use the polar coordinates, but if you use the polar coordinates, it's kind of straightforward. Any question, guys, about this example? Okay, so so the conclusion here is that, of course, both my vector line integral along this closed boundary is equal to this double integral over d dx dy. So both are equal to 8 pi. All right, so this is for the first exercise. As I said, we had like a 3 exercises or 3 problems, 3 different problems. The second exercise is kind of similar to this one. Is again, you have to verify the Green's theorem. But I mean, it would take a lot of time, I guess, to do the exercise number 2. So I'm gonna do just the number 3, okay? Because as you can see, I spent like at least I would say 30 minutes in this problem and this first exercise. So I'm gonna just do probably the exercise number 3. The exercise number 2 is very similar to this one. 3 is kind of different. Well, it's not that different, but in number 3, exercise number 3, we said we had to. So this is number 3. Exercise number 3. So in the exercise number 3, this is you have to use Green's theorem to find the area between the ellipse x squared over 9 plus y squared over 4 equals to 1, and the circle x squared plus y squared equal to 25. So this is, I would say this is, I think there's a similar problem in the homework. Let me see what would be the problem. Is there? No, I don't think there is a similar problem. In the homework. Okay, you don't have to find the area of some region using Green's theorem in the homework. But anyway, let me remind you here, because this is one of the, I'll say, really nice consequence of the Green's theorem. So how do we use Green's theorem to find the area of some region? Well, so let me just remind you of the remark we had the last time. So the remark is the following. So remark. So let's say f, vector field f is equal to minus y and x. So this would be m, and this would be n. All right. So when you do half of the vector line integral of f ds along the boundary of your region D. So this is half. Derivative. So this would be equal by Green's theorem. So I'm going to apply just Green's theorem here. Write down here for you. So that will be equal minus, y, the first component of f minus y dx plus x dy. Okay. So that will be equal, if you use now Green's theorem, so if you use Green's theorem, well, before that, let me just remind you guys why I can write this, why this is minus y dx plus x dy. Well, because, well, f is minus y x, right? ds, this is, ds is the infinitesimal displacement. So ds is supposed to be dx dy, okay? It's a vector. So ds here, it's not the length element of the curve, it's the infinitesimal displacement of the curve. So it's a vector. So it's given by dx dy. So when you do the scalar product, so it's minus y times dx plus x times dy. Okay. So if you use Green's theorem, so that will be equal to half the integral over the region D of, well, derivative of n with respect to x. So n is x. Derivative of n with respect to x would be 1 minus derivative of m with respect to y. So that'll be -1. So minus -1 dx dy. So 1 minus -1, that would be 2. So that's half double integral over d of 2 dx dy, which is of course equal to the what's the integral of double integral over d of 1? Half times 2, that would be 1, so dx dy, and that's exactly the definition of the area of D. Okay. So again, what we are saying is that the area of D, if you want to use Green's theorem, you can say that the area of D is equal to actually half of the vector line integral minus y dx plus x dy. Okay. And we said, I mean, this is very nice because it gives you like a relation between the area of a region, which is, some two-dimensional notion. The area, it's a two-dimensional notion. Okay. So it relates a two-dimensional notion to a one-dimensional notion, which is just the vector line integral along the boundary. Okay. Anyway, so in this case, you want to compute this area of D using Green's theorem, so you have to evaluate this vector line integral. Okay. Anyway, so I don't think I will give you all the details here because I think it's going to be a lot of computations here. But I'm going to just show you how to compute this vector line integral. So first, I mean, you have minus dx plus x dy here, which is nice. It's very explicit. We know what it is. Now, the problem, of course, as usual with these vector line integrals, is to parameterize this boundary, right? That's always a problem with so we have to parameterize the boundary of D. Okay. Now, so now what's this boundary of D? Well, if you sketch D, so what's D? D is sketch D and the boundary of D. Okay. So D is, we said, is the region between the ellipse and the circle. So we have so first we have the circle 2, 3, 4, 5. 1, 2, 3, 4, 5. So first we have the circle x squared plus y squared equals to 25. Right. So we have this circle here. Right. This is x squared plus y squared equals to 25. And then we have the ellipse x squared over 9 plus y squared over 4 equals to 1. So if y is 0, then x, for example, would be 3. And if x is 0, y would be 2. So the ellipse would be this one here. Right, so this is x squared over 9 plus this y squared over 4 equals to 1. Okay, and so the region D is the region between the circle and the ellipse. So my D is this region here. This is my D. Okay, that's my region D. And so what would be the boundary of D? Well, the boundary of D, of course, would be given by these two circles. We have the first circle here, this one here, outside, this one here. So this is, let's say, C1. That's my circle. So it says C1 here. And then the second piece of the boundary would be the ellipse, right? This is the second piece of the boundary, the ellipse, right? Let's call this ellipse C2. Okay. So what I'm saying here, guys, is that the boundary of D would be equal to the union of the circle plus the ellipse, right? So the boundary, oops. So C, which is the boundary of D, is the union of C1 with C2. Okay. So that's the boundary of D. Now, don't forget, you want to apply the Green's theorem, so you have to orient your boundary so that the region D would be on the left, right? So for C1, you have to pick an orientation for C1. So then you need D to be on the left, right? So then you have to orient your circle using a counterclockwise rotation, right? Like this one here. Right. So then D would be on the left as one traverses the circle. Okay. Now, what about the rotation of the ellipse? So again, the D would be on the left, so you need a clockwise actually orientation for C2. So because you need D to be on the left. So this would be the right orientation for the ellipse. Okay. Now, so you need to parameterize the boundary. So let's first parameterize C1. C1 is just a circle. So whenever you have a circle, then you can just use cosine and sine. So in this case, it's the radius is 5. So then the parameterization here would be 5 cosine of t, 5 sine of t, with t between 0 and 2 pi, of course, because it's a whole circle, as usual. Of course, again, this is because this is like supposed to be your x of t, and this is supposed to be your y. And if you do x squared plus y squared, that will be 25, right? This is the parameterization of your circle. And actually, this parameterization coincides with the given orientation, right? Because as I explained in the previous example, if you take gamma of 0, that will be the 0.50. And if you take gamma of pi over 2, that will be the 0.05. So that will give you a counterclockwise rotation, right? So the orientation here is the correct one, so with the right orientation. Okay. Now, what about C2, the ellipse? Well, ellipse, how do we parameterize the ellipse? It's the same idea, of course. I mean, ellipse is just a sort of twisted circle. So we're going to use the cosine and the sine, but with different coefficients. So for C2, let's say beta of t, you can say, well, it's 3 cosine of t, 4 sine of t. That's because, so this is x, this is y. So if you do x squared over 9 plus y squared over, where is it? Sorry, it's 2 here. This is 2. So if you do y squared over 4, that will be equal to, 3 squared over 9 cancel out. The 2 squared over 4 cancel out. So it's going to be just cosine squared plus sine squared, and that will be equal to 1. And that's exactly the equation of my ellipse, right? X squared over 9 plus y squared over 4 equals to 1, right? And t, would say t is between 0 and 2 pi. Okay. But then here, there is a problem, okay? So the problem is with the orientation. So here you have to be careful. So there is a problem. So I claim that there is a problem with the orientation. So this would give you the counterclockwise orientation, and that's not the orientation required by Green's theorem, right? So like in this case, if you do, let's say beta of 0, if you do beta of 0 would be equal to 3 0, and if you do beta of pi over 2, that will be equal to 0 2. So we are moving from 3 0 to 0 2. So this is 3 0, and this is 0 2. Okay, and so if you move from if your particle is moving from 3 0 to 0 2, then actually you're gonna have a counterclockwise rotation, right? If you move from 3 0 to 0 2, you're gonna have a counterclockwise rotation. So you need to move from 0 2 to 3 0, right? That will be the clockwise rotation, right? So there's a problem with this parameterization because the induced orientation is not the one required by Green's theorem. So there's a problem here. So that's not. So here, of course, you're moving from 3 0 to 0 2 because, because well, 0 is less than pi over 2. So you start at time t equals to 0, and then you're going to have time t equals to pi over 2, right? So you think of the parameter t as a time, right? So at time t is 0, I am at this point, and at the time t pi over 2, I'm at this point, right? So so this is the wrong orientation. So I need to change my parameterization, okay? I need to make it a clockwise rotation, right? And the idea to do it is just to take, in this case, like for circles or for ellipses, all you have to do, guys, is instead of having t, you can change it to 2 pi minus t. Pi minus t here. And then 2 pi minus t. Okay. So now, if you evaluate beta of 0, okay, so if you evaluate beta of 0, of course, that will be just the same thing. Beta of 0, that will be 3 equals sine of 2 pi, 2 sine of 2 pi, which is again 3, 0. Okay. But let's see what happens when t is pi over 2. So if t is pi over 2, then that will be 3 equals sine of 2 pi minus pi over 2 pi minus pi over 2. That will be 3 pi over 2. And here also 3 pi over 2. Now, of course, cosine of 3 pi over 2 is 0, but sine of 3 pi over 2, it's not 1, it's negative 1, right? And that will be negative 2. So what I'm saying now is that my particle is moving from phi 0 to, from phi 0 to 0, negative 2. So in other words, if, so here is, this is of course a 0, negative 2. So what I'm saying now is that I'm moving from phi 0 to 0, negative 2. And that's the clockwise rotation, right? And that's exactly like one side with the required orientation, right? So you see the difference, guys? Yeah, so that would be the correct orientation. Okay. So here, so be careful. Just you have to check the orientation, make sure that you have the correct orientation. Okay, because otherwise you would have a problem with the answer. Of course, you will end up with the wrong answer, because you're gonna end up with there's a minus sign, which will change your answer. Okay. Anyway, so once you have this is the parameterization for your curves, the curve C1 and C2, and then you can just evaluate your vector line along these two curves. Okay. So in other words, your area of D would be equal to half of this the integral over the closed curve C1 of minus y dx plus x dy, and then then you plus again half. So the second piece of your boundary is the ellipse, this is the C2, and again you're going to have to integrate the same vector field minus y dx plus x dy. Anyway, guys, it would take probably another 30 minutes just to finish this computation. So I'm gonna just, I think I have the answer. You can try this at home later, but the answer would be 20. I think it's 26 pi if I'm not mistaken. Okay, so this is here are the long computations. But now at this point, we should know how to compute the vector line integrals. But what's really important, I guess, here is like to find the parameterization of your curve with the right orientation. Once you have parameterization and the right orientation, then I think you are good to go. Okay. All right, guys. Is there any question? Any remark? Okay, so before, so let's finish this Green's. Oh, we are not done yet, actually, with this Green's theorem. I want to mention another, a different reformulation of Green's theorem, because this different reformulation of Green's theorem would generalize to Stokes' theorem in this space. So I'm gonna just, so there is another way actually to state the Green's theorem. So let's just finish with this remark here. So this is different. This is a different reformulation of Green's theorem. I'm going to use actually vector reformulation. Okay, so different reformulation of Green's theorem. Okay, so again, our Green's theorem, the formula is the following. So we have this vector line integral over the boundary of your region D of your so vector field F. We said this is equal to F, of course, is given by these two functions M and N. So here the vector field is defined on in R2, right? This is in the plane. In R2, the plane. Okay, we have only two variables here over D of this partial N, I think, partial X, partial M, partial M, partial Y, dx dy. Okay, so this is the formula for our Green's theorem. So as I said, I'm going to just mention another different reformulation. It's a vector reformulation of Green's theorem. So this is vector reformulation of Green's theorem. So what we can do is the Green's theorem. So here we have only two variables, right? X and Y. Now, if you just if we are in the space, of course, then your vector field F would have three components, right? I mean, in the plane, we have two components. I mean, vectors, they have two components. Now, if you are in the space, so we are in the space. Okay, so this vector reformulation of Green's theorem is going to be in the space. So space, which means, of course, R3. Okay, so I'm going to write my vector field F. So my vector field F would have now, so my vector field F would have three components. So we're going to have M, of course, as first component. As second component would be N. But as third component, because, well, there's no third component in F. It's just in the plane, right? So I'm going to just say it's 0. The third component of F is 0, right? Okay, so now this F is defined, this vector field F is defined in this space. I'm just saying that the third component is just 0, okay? Again, initially my vector field F, the Green's theorem, is in the plane. We have only two variables, two components, but now I'm gonna consider, I'm gonna try to reformulate this Green's theorem in the space. So now we have three, three variables, and so we have three components, and so my F, I can write my F like M, N, and 0. Now there is another vector field, a very interesting vector field, which is called nabla. So this nabla, so this is nabla. Of course, it's just a Greek letter. This nabla is actually equal to, is defined as the vector partial X partial y, partial z. Okay, so this nabla here is actually, it's called the del operator. Okay. I mean, it's a, you can see this nabla as a vector field. So it's given by three, it has three components. So it's a vector field. Now, if you do nabla cross product, so this nabla here cross product with f. So this is here, this is not the scalar product, it's the cross product, right? I guess you have seen this cross product in Calc Phi. So in this space, you have this notion of cross product. So we have this cross product of nabla, this del operator, with this vector field f. And actually, this cross product of nabla with this vector field f, it has a name. It's actually called the curl of f. So this is called so nabla cross f. This is called the curl of f. Okay. If you took some physics course, I think probably you have seen this this notion of curl of a vector field. But the curl of a vector field actually measures, I mean, in general, it measures the twisting or the circulation of the vector field f. So in other words, so this thing here, this curl of f, it measures the twisting of f. So what do I mean here? Measures the twisting of f. So for example, you have some, so you have some object and it's moving along, let's say, a circle, but it doesn't rotate. It's gonna, let's say this object here is gonna keep the same position, right? So here's, it doesn't change it doesn't rotate, right? Okay. It's always like it has always this diagonal direction, for example. Okay, so in this case, this object here along the circle, it doesn't rotate, all right? It doesn't, so there is no rotation or twisting of this object along this circle. So we say in this case, for example, the curl of this object would be 0, okay? Because it doesn't, it doesn't really, the object itself, it doesn't really rotate, okay? So if you have, let's say, if you twist your object, like this line here, becomes like this here along this circle here. So in this case, the curl is not 0. Okay, so that's what I mean by it measures the twisting of this vector field f. Okay, so vector field f, you think of vector field f at a point as, it's a vector. You have some direction, right? So if you keep always the same direction, then the curl of your vector field f would be 0. If you change the direction of your vector field, okay, along the circle or something, okay, then the curl of f in that case would be not 0. Anyway, as I said, if you took some physics course, you should see this notion of curl of a vector field. But how? So this is, as I said, cross product of this nabla del operator with the f. So this is just it's given by the matrix. So we have I, J, K. The first, the second, in the second row, we're gonna have nabla. So we're gonna have partial x, partial y, partial z, and in the third row, we're gonna have f. So that's m. This is n, and this is 0. Okay. Of course, I, J, K here. I is just the vector 1, 0, 0. I is just the vector 1, 0, 0. J is the vector 0, 1, 0, and K is, of course, 0, 0, 1, right? So if you remember how to do the cross product, so you take So you're supposed to take like the first column, first row, first column, multiplied by the determinant of this matrix here, right? Okay. Anyway, so and then you have plus, you take this here, then you have to multiply by the determinant of this matrix here, right? And then there's k, okay, multiplied by this here. Okay. Anyway, so what I'm saying, guys, here is that if you do, so that will be equal to, for I, you're gonna have 0, and then you're gonna have n, derivative of n with respect to here, right? So this is derivative of 0 with respect to y, of course, 0. Derivative of n with respect to z. So we're going to have derivative of n with respect to z times I, minus here, I guess there's a minus. Now for j, we're going to have, let's say a plus. And for j, we're going to have, derivative of m with respect to z, j. And then for k, we're going to have derivative of n with respect to x minus derivative of m with respect to y, k. Okay. But the thing is, m and n, they are just functions of x and y, right? There is no z in m and n, right? So this derivative of n with respect to z is just 0 because there is no z in the functions m and n. They're just they depend only on x and y. So this is just 0. This is only 0. This is also 0. And so what I'm saying in this case is that if you do the curl of f in this case, that will be equal to partial n, partial x, minus partial m, partial y, times the vector k. Again, k is the 0, 0, 1. And you can see this is exactly this partial n, partial x minus partial m, partial y. That's exactly the right side of my Green's theorem, right? In Green's theorem, on this in this double integral, the function here to integrate is partial n, partial x minus partial m, partial y. So that's exactly what I have here, right? When I do this curl of f. Anyway, so this is a vector, of course. When you do a cross product, this is like saying this would be the vector. So this is a function here, and you are multiplying this function by this vector, function times a vector. Okay, so it's like saying, you have this partial n, partial x minus partial m, partial y times the vector 0, 0, 1. Right, that's my k. It's 0, 0, 1. And how do we multiply a function by a vector? I mean, if you have a scalar, you have a number and you multiply a number by a vector, you have to multiply each component of the vector by that number. Okay, so in this case, we have a function. So what we do is we are supposed to multiply first component by this function, second component, same function, and the third component by this function. But in the first and second component of the vector, they're just zeros. So it's going to be just equal to 0, 0, and then the difference between a derivative of n with respect to x with a derivative of m with respect to y. Now, this is a vector, right? When you do cross product, when you do scalar product, you get the number or you get a function. When you do a cross product, you get a vector. Okay, so now if I want to get just this function here, partial n, partial x minus partial m, partial y, what I can do is I can take, So my cross product, the curl of f, okay, this is vector, which is equal to exactly this here, right? And scalar product with a vector k, which is 0, 0, 1. So here, this is a scalar product. This is a vector here, and this is also a vector. So if you do scalar product with k, and k is just this is just the vector 0, 0, 1. So you're gonna have that will be equal to 0 times 0 plus another 0 times 0 plus this function here times 1 times this one here. So that will be partial n partial x minus partial m partial y. So all I'm saying, guys, is that if you do, so the conclusion here of this computation is the following. So conclusion is that if you do the curl of f, well, you don't need the arrow here over nabla. Curl of f, scalar product with the vector k. Again, k is just the vector 0, 0, 1, right? That will be equal to the function partial n partial x minus partial n partial y. Okay. So in other words, I can write the double integral over d and using this cross product. So then, so the conclusion is that, so here's my vector reformulation of Green's theorem. So what we are saying is that the vector line integral of f, the vector field f along the boundary of D. Okay, this would be equal to, so it's supposed to be double integral over D of partial n partial x minus partial n partial y, but that's actually equal to the curl of f scalar product with the vector k. Okay, dx dy. So here's dA. This is just the area element. This is the area element here. Okay. So basically what this formula says is that, so on the left side, you have this vector field F along this boundary of D. So that would be like sort of the circulation of the vector field F along the boundary. So, so the idea here is that, so this left side would represent, that's just the circulation of F, of the vector field F along the boundary. Okay. And the right side, as I said, this curl of F is supposed to represent like it measures, you know, the twisting or the rotation of your vector field, right? So the right side would represent like the total, in some sense, the total, you know, the total infinitesimal twisting or rotation of F, twisting or rotation of F over the entire region, over D. Region. I mean, this is like sort of you know, an interpretation of the Green's theorem. Okay, sort of geometric interpretation of Green's theorem. Okay. Anyway, so yeah, so this vector line integral is just equal to this. So this is the curl of F, as I said. It measures the twisting of the circulation of F over, you know, in this case, over the entire region D, right? This is the curl of F. Okay, so why I'm doing this, I would say why I'm doing this reformulation of Green's theorem. Well, because we're gonna generalize this reformulation. So this is your capital F here, your vector field F here has only, it's just M, N, and 0, right? You remember capital F here? Well, we are in the space. So capital F is just M, N, and 0. So what we're gonna do next, guys, in Stokes' theorem, we're gonna generalize this reformulation to the space. So then your vector field F would have like 3 components. Let's say M, N, and I don't know, L. Okay. So in Green's theorem, your F has only 2 components, M and N. And of course, the third component in the space would be just 0. But in Stokes' theorem, we're going to have 3 non-vanishing components. So we're going to have M, N, and a third function. Okay. So again, so we are doing this because, so we're going to generalize. So the point is that we're going to generalize this reformulation. So the idea here is that, so we're going to, I think in section Stokes' theorem, that's a section, let me see, which section is that? Stokes' theorem. Yeah, 8.2. So we're gonna generalize this reformulation to, F having like 3 components, like M, X, Y, Z, N, X, Y, Z, and L, X, Y, Z. Okay, and so that would be Stokes' theorem. So the generalization is going to be the Stokes' theorem. That would be Stokes' theorem. Okay, so this is section 8.2. Of course, Stokes is a famous, physicist, right? And also mathematician. Anyway, guys, is there any question? Again, this is just this reformation here is just because I want to make a link between the Green's theorem and the Stokes' theorem we're gonna see in later in the section 8.2. Okay. Is there any question, guys? All right. So otherwise, I guess we have how much time? Yeah. Okay. 20 minutes. Well, actually, there's also another formulation of Green's theorem, but probably I'm not going to do it because of the time, and probably you don't really need it. But let me just say something here about this operator nabla. I mean, just for your information, so you have these notations in physics. So you have this nabla, right, which is this del del x, del del y, del del z. Okay, let's say you have this vector field f. It's given by 3 functions. I don't know. Let's say m x y z, n x y z, and l x y z. Okay, so we said if you do nabla, which is a vector cross product with the f, that will be the curl of f. It's called the curl of f. So this is a cross product. Another possible operation you can do, of course, between 2 vectors is the scalar product. So if you do nabla scalar product with f, okay, you have 2 vectors and you can decide to do the scalar product, right? This is here in this case, this will be the scalar product. And so the scalar product is actually called the divergence. This is a scalar product. This would be the divergence. We come back to this notion of divergence later, because that will be the Gauss divergence theorem. But let me just say here, if you do the scalar product between this nabla and the vector field F, that's called actually the divergence of F. Okay, and there is a third, I would say a third notion, probably you have seen in the Calc 3. Now, if you have just a function F, so F, let's say, is just some function of X, Y, Z. So if you have nabla F, okay, this is just a, this is just a partial F, partial X, partial F, partial Y. So here F is lowercase f, okay? It's just some one function, okay? Partial F, it's not a vector field, it's just a function, right? Partial F, partial Z. This is called the gradient of F, okay? This is called the gradient of F. Gradient of the function F, okay? Okay, so this is like different terminology. I don't know if you have seen this gradient of F. I think you have seen it in Calc 3. That will be the gradient of F. But yeah, so with the vector fields, when you do the cross product with this nabla, that's called the curl of F. And when you do the scalar product, that will be the divergence of F. Anyway, so this is just for your information, and I will come back to later to this notion of divergence with the Gauss theorem. But okay, so what I'm gonna do, guys, in the, let's say in the last 15 minutes, well, I'm gonna start probably a new section. So we are done with the Green's theorem. I think I gave a lot of details here about this Green's theorem, because this is one of the most important theorems in vector analysis. Actually, the three main theorems in vector analysis are Green's theorem, Stokes' theorem, and we're going to see there this is a Gauss divergence theorem. Okay, so I'm going to move to the next section, unless there's a question or any remark about this Green's theorem. Okay, so then let's move to the section. So I'm gonna make like a jump, and I'm gonna go to the section 8.3, because it's kind of related to the Green's theorem. So so this is section now 8.3, conservative vector fields. Okay, so what's the problem here in this section? Well, guys, as we discussed in section 7.2, right, when we discussed the vector line integrals, we said that the vector line integrals depend only on the underlying curve and its orientation, and not on the particular parameterization of the curve, right? And so we said at some point we proved, we discussed that we said that the vector line integrals, they are independent, right, of the parameterization of the curve, right? So if you change your parameterization of your curve, it doesn't change, your vector line integral. Okay. Of course, if you keep the same orientation. If you change the orientation, then you're gonna get the opposite answer, right? So what I'm saying is that in section 7.2, when we discussed this vector line integrals, we said, so vector line integrals are independent independent of the parameterization of the curve. Okay. Okay. But they depend, of course, on the orientation, and of course, they depend on, are independent of the parameterization here, independent of the parameterization of the curve. So what I'm saying is that if you reparameterize your curve, you choose a different parameterization of your curve, then you're supposed to get the same answer. Okay. Actually, however, in some special cases, even even the curve itself doesn't matter. Okay, so there are some special cases, and some special cases actually special cases, and I'll give you a couple of examples. So in some special cases, even the curve itself doesn't matter. Even the curve, not just the parameterization, but even the curve itself doesn't matter. Okay. What matters here only the initial and the terminal points. Okay. Only the initial and the terminal points. Only the initial and terminal points matter. Okay. So I'm going to give a couple of examples, but actually, before the examples, so I'm going to give you the definition of this. So here I'm saying there's some cases where the vector line integral doesn't even depend on the curve itself. So that's what we call actually path independent line integrals. So I'm going to define this notion of path independent line integrals, and I'm going to give you a couple of examples. So what I call so this is path independence. So if you have a continuous vector field, so a vector field F has a path independent line integrals if the integral of f along a curve C1, if the integral of the vector line integral of f along C1 is equal to the vector line integral of f along C2 for any two simple oriented curves having the same initial and terminal point, having the same initial and terminal point. So what I'm saying, guys, is that so I have 2 points. I have let's say I have this point A. This is my point A, right? And I have this point B. Okay, so there are infinite number of curves connecting A to B, right? So for example, we can have this curve C1 here, right? You can have another curve. Let's say here's another curve C2. There's a third curve. Let's say this one here, C3. Right. There are infinite number of simple and all of them, they are supposed to have, so you're going from A to B, right? So the first curve here, the orientation would be this one, of course. C2, you'd have this orientation here because you're going from A to B. Here's C3. Okay, so you can imagine, of course, you can have also another curve here, C4, connecting A to B. So you're moving from A to B, right? Anyway, so you have infinite number of curves connecting A to B. And what I'm saying, guys, is that a vector field F has this path and dependent line integral if the vector line integral over over any curve connecting A to B would be the same. Okay, so so what I'm saying is that so F has path and dependent line integral if if the integral of f along C1 is the same as the integral of f along C2, is the same as the integral of f along C3, etc., etc., etc. All right. So all I'm saying here is that if your vector field has this path and dependent line integrals, then your integral, it doesn't depend on the curve itself. It doesn't matter the curve, right? You can take the curve C1 or the curve C2 or the curve C3, etc. But then you're going to get always the same answer. And actually, as I said, what matters here is just the initial and the terminal point. Okay. So the curve itself, it doesn't matter. You can take any curve here, C1, C2, C3, or C4, etc. Then the integral will be the same. You're gonna get the same answer. Okay, so it's independent of the curve you are taking, right? So that's what I call path independent line integrals. It only depend on actually it's gonna only depend on the initial and terminal points. Okay, so let me give you an example. Example 1. This is example 1. In the last 5 minutes, I'm going to give you an example 1 here. So I'm going to take a very simple vector field F. So let's say f of xy is equal to xy. Okay, that's my vector field F. It's just xy. Okay. Actually, we will prove later that this vector field has path independent line integrals. But let's see if you take, this is x, this is y. Let's say this is 0, 0 here, and here's the point 1, 1. Okay. And I'm going to take 2 curves going from 0, 0, moving from 0, 0 to 1, 1. I'm going to just first, I can take, for example, the parabola. So let's say C1. Okay, so this is C1, and this is given, it's a portion of the parabola y equals to x squared. Okay, so you're going from 0, 0 to 1, 1. Of course, if x is 0, y would be 0. And if x is 1, 1 squared would be 1, right? So the first path here I picked is just the portion of parabola y equals to x squared. And we are moving, of course, from 0, 0 to 1, 1. Okay, so I'm gonna take another path. Let's say another path along. So the path along the y-axis first. Okay, and then this horizontal line here. Okay. This is another path, connecting connecting 0, 0 to 1, 1, right? This is my path C2. Okay. And I'm gonna compare the vector line integral of f along C1 to the vector line integral of f along C2. Okay, so along C1, so I'm gonna compare vector line integral of f along C1 with the vector line integral of f along C2. Okay. Along C1, well, so we know f, of course, is just this xy. So we have to parameterize C1, right? That's the missing thing here. So what's C1? C1 is just the parabola. So we have to parameterize C1. Which is just a portion of the parabola y equals to x squared. So we can say, for example, if we say x is t. So if, for example, x is t, that would be the simple probably choice. If x is t, then of course y, which is x squared, would be t squared. Okay, so one possible parameterization of this curve C1 would be, so C1 is given by, let's say, the following parameterization. So gamma of t, x is equal to t, and y is equal to t squared. So here's my t squared. Okay, this is my x, and here's my y. And t, so we are going from 0, 0 to 1, 1. So t is just from between 0 and 1, 1, right? Sorry, it's 0 and 1. So when t is 0, you get the point 0, 0. When t is 1, you get the point 1, 1, and you are moving from 0, 0 to 1, 1. Okay. So if you want to compute this vector line integral along C1, f ds, so that will be equal to f of gamma t scalar product with gamma prime of t et. T is from 0 to 1. So what's f of f is just equal to xy, right? So that's the vector field. X is t and y is t squared. Gamma prime of t, so derivative of t is 1, derivative of t squared is 2t, right? dt. This is a scalar product, so that will be 0, 1, t times 1 is t, plus t squared times 2t, that's 2t cubed, right? dt. You integrate this, right? You integrate this. This is just t squared over 2 plus t cube. Sorry, t to, so it's 2t cube, of course. So the integral would be t to the power 4 over 2. Okay, evaluate between 0 and 1. That would be half plus half. That would be 1. So the answer is 1. Okay. Now, in just 1 minute, guys, for C2, we want to parameterize C2. So then C2 is, well, it's actually, it's a combination or a union of two curves. This one here, and this one here, okay? Anyway, so probably I'm going to leave this for next time. But I claim that the answer vector line integral of this vector field f along the C2 would be also equal to 1. Okay, so both are equal to 1. Of course, to establish that this vector field has path-independent line integral, we need to check that the value of the line integral of f along any choice of path between the 2 points is the same as any other. Okay, so this is not enough. I mean, we are comparing these two line integrals. They are equal. It doesn't mean that this f has a path-independent line integral, right? Because we have to check this dependency, right? For along any choice of path, not just these two, but for any choice of path. Okay, and that's of course really hard, but we'll see a theorem that will allow us to, to check if your f has a path-independent line integral. Anyway, guys, I'm gonna stop here, I guess, and I'll continue with this conservative vector field next time. And please don't forget your homework number 4. So it's due this Thursday. And of course, if you have any questions, just email me anytime. All right. So I guess I'm gonna stop recording.